This lesson is addressing the concept of calorimetry. But I wanted to start off by just thinking about maple syrup. It's a great way to do it. When I was a boy, my father showed me that if you snap the end of a twig on a maple tree when the syrup was running and you left it overnight, so the key idea with maple syrup is that the sap runs the best when you have above freezing temperatures during the day and below freezing at night. So if you snap a twig and it gets cold overnight, then as the sap runs, it forms an icicle, which we used to call a sapsicle. So yep, that's what I would do is I'd make sapsicles and they would be delicious, very sweet. Native Americans knew this, of course, and at the time the trees were running with sap, it's a really joyous time because it means you survived winter and the ground is about to come alive again. So one of the ways in which Native Americans made maple syrup is that they would take stones and put them in a fire and let them get really, really hot. And then out of a hollowed out piece of wood or something like that, they'd put maple syrup in that they had collected and then drop the rocks in. So we're going to take a look at this from the point of view of calorimetry, and we'll do some experiments. So the whole point with calorimetry is that Q heat causes a temperature increase based on how much stuff you have, what stuff you have, that's heat capacity, and then a temperature change. But the Native Americans were trying to evaporate water and leave behind a thickened syrup. And so they also were counting on this, where heat can also go into vaporization. Right. So here's our experiment. In scenario one, let's start off with, say, a liter of sap, and we'll call it water. So on the sap side, we're going to have 1 liter, and the heat capacity is going to be equal to the same thing as water, so 4186 joules per kilogram degrees C. And for our rock, let's use maybe 200 grams, so 0.2 kilograms. And the heat capacity on the average for the Earth as a whole is about 2,000 joules per kilogram degrees C. And for initial temperatures, we'll start off with a sap at, I don't know, let's say not cold, but also not warm either. So about room temperature, so 20 degrees C. And for the rock, if this just came out of a wood fire, and of course these temperatures can vary quite a bit, but let's suppose about 600 degrees C, which would be approximately the temperature of some moderate coals at the base of a fire. But what we don't know is what the final temperature is going to be equal to. Okay, well, what's going to be happening is that we're going to have the sap, which is essentially cold stuff. And then the rock, which is the hot stuff. So when the rock is plunged into the sap, the rock is going to give off heat and the sap is going to absorb it. Now, as always with these calorimetry experiments, they're very messy. It's hard to control because our system is frequently including other things like the wood, the air around it, whether we've got radiation happening and all sorts of things. But so we'll just simplify things. So conservation of energy, one of the great laws of science, says that QH plus QC, this is the heat lost by the hot stuff and the heat gained by the cold stuff, is going to be equal to 0. This is a basic conservation of energy statement. So the hot stuff is going to lose heat, primarily because when we do delta T, the final temperature is lower than the initial. So this delta T for the hot stuff is going to be negative, and the delta T for the cold stuff is going to be positive. Right, so let's spell it out. We'll use R for the rock. So this is going to be MRCR, and delta T, which is TF minus TI, plus M, we'll use S for syrup, C for syrup, TF minus TI is equal to 0. All right, well, let's put in some numbers here. So for the rock, we're going to have 0.2. I'm expanding this out because we're going to need a little more room. And then 4186. Yep, sorry. 2000 is what I meant. Oh no, I made a mistake. Shoot. And then TF, we don't know. But the initial temperature is 600. Plus, now we're talking about the syrup and we're treating it as so much water. 1 liter has a mass of 1 kilogram. So that's going to be 1 times 4186. The final temperature we don't know, but these two will be the same. So we're only solving for one variable. And then minus 20. And then that's equal to 0. All right, so let's do some math. All right, calculator, my old friend. So let's do 0.2 times 2000. 400, of course. So 400 TF minus, and then we'll multiply that same 400 by 600. And of course, we're going to be dealing with big numbers because a joule is a very small unit of energy. So at this point, yes, we're just talking about units of energy. Plus 4186 TF and then minus, and then we'll multiply 4186 times 20. The heat capacity for water is very high because of the very strong intermolecular forces. It takes a lot of energy to, it's lots of degrees of freedom. So when you sink energy into it, the temperature doesn't increase very much because there's lots of different degrees of freedom that can share that energy. So now, that's why this number is much bigger. The water definitely dominates. So we can combine like terms and then solve. So 4586 TF minus, and then we'll just add these two together. So I can just add 240, 1, 2, 3. So that's 3, 2, 3, 7, 2, 0 equals 0. So add this to both sides, divide by 4586. And so our final temperature is equal to 70.6 degrees Celsius. I did that kind of fast. Let me just do it out again so you can see. Oh, 77. Ah. Wow, 2 mistakes on the same lesson. That's not good, Joe. So 77.3 degrees Celsius. All right, great. So now we made it hot. What if we add another rock? Add another one, says DJ Khaled. Right, if we add another rock, what's going to happen? Well, here we have to slow down a little bit. So the temperature increase from 20 up to 77.3 is 57 degrees. If I add another rock, then the temperature increase is going to hit 100 degrees. So we actually have a bit of a problem here. So the temperature is only going to increase to 100 degrees, and after that, vaporization happens. So we need to build that in. So what's going to happen is that when we do QC for the cold stuff, we're actually going to have two terms. We know that our final temperature is going to be 100. But then we're also going to need a term for how much water is going to boil away. Okay, well, let's go ahead and set that up. So QH plus QC. So let's go. So mass of the rock. And we'll do this where we'll just put in the rock value as being 0.4, and we'll start from 20 degrees again. So MR CR times TF minus TI plus the mass of the syrup and the heat capacity of the syrup times TF minus TI. And we know the final temperatures are going to be 100. And then plus MW, which is the mass of the water that boils away, times the heat of vaporization for water, and that's all equal to 0. So again, we know what the final temperature is going to be. So if we're starting off with the water at 20, then the mass of the rock, we're adding 2 rocks in this time. And so that means the mass is going to be 0.4. So 0.4 times 2000. And again, we know because we got a 57 degree temperature rise the last time that we're going to hit 100. So the final temperature is going to be 100. And the initial temperature of the rocks, because they just came out of the fire, is 600. Plus the mass of the syrup, which is 1, times 4186 times the final temperature is 100 minus 20 plus the mass of the water that's going to evaporate times 2260. And here's where we have to be careful, because in a chart it said this was kilojoules per kilogram. So to get the units to match up, we're going to have to add in 10 to the third in order to get it to be joules per kilogram. Very sneaky on that chart. All right, well, the nice thing is that we don't have to do the distributed property. Things should sugar out nicely. Get it? Pun, sugar off. Indeed, times 2000. And then times -1, 500. Okay, so -4 and lots of zeros. Plus, and again, negative because the rocks lose heat. So 4186 times 80 plus mass of water and times 2260, and then I'll just add it in instead of having scientific notation. Great. So these just add up, which is great. So I'm going to subtract 400,000 from the number I just calculated. So minus 65120 equals, oops, sorry, plus 2260123 times MW equals 0. And so we add this to both sides and then divide. And so M is equal to 0.02, and I'll round it off, 29, and that's kilograms. So 29 grams evaporates. Well, we got a big temperature increase when we added one rock, but adding a second rock, we only evaporated 29 grams, right, out of 1,000 that are there. So we only evaporated 2% of the water that was there. And to get maple syrup, we probably need to evaporate something like this. Yeah, we need to evaporate about 97% of the water that's there. So that's going to take a few rocks. But if you're just sitting around and you don't have very much to do, you could probably make maple syrup in a day. All right. So a good lesson, we talked about a simple calorimetry situation. And we also said, what happens when calorimetry butts up against phase change? All right.